Hello out there. The original tape of this lecture was somehow messed up, and so we're retaping it for our worldwide viewing audience. There's actually, hopefully, an advantage to this retaping. We're going to have better technology since we're in a very specially made-up room, and hopefully the equations will all come across as quite viewable on the web. So we're hoping this will work quite well, and we'll see. Today, I want to do two things. First, we will be going over the problem set on Probit, which I assume all of you have done, and discuss the results that were obtained. And then after that, we will talk about Mixed Logit, do a discussion lecture on Mixed Logit. So those of you who don't want to hear the part on the Probit problem set can just skip ahead on your real player and go right to the part on Mixed Logit. It will be indicated on the web what minute that starts. Okay, so let's talk about the problem set for Probit. The first thing that you were going to do was to examine the program that was written, probit.txt, and make sure you understood everything that went on, and then to run the program and get the results. So first of all, let's talk about what the results are and what they imply. The first five set of parameters, the first five parameters are given here. We're not going to really discuss these. These are just the standard ones that you'd have in any discrete choice model. You've got the price coefficient, the time coefficient. Remember that was scaled, so if you're figuring out willingness to pay, you have to capture the scaling. And then dummy variables for carpool, bus, and rail. Obviously, carpool, independent of time and cost, is the least desirable mode. Bus is next, and rail is next to best. The best one, of course, is car alone, because it's the one that's held to zero by normalization. So these are the coefficients of the explanatory variables. There are also, however, the parameters that are associated with the covariance matrix. These are the estimated coefficients or parameters of the covariance matrix. Each of these is an element of the Cholesky factor that we were estimating and that is described in the problem set setup. Okay. What this translates into is a Cholesky matrix that has these as its lower triangular elements. This is the Cholesky matrix that is implied by the coefficients. This is the fifth parameter estimate, 6th, 7th, 8th, 9th. I'm sorry, 6th, 7th, 8th, 9th, 10th. So all of those parameters that you estimated just enter into the Cholesky matrix in sequential fashion. The covariance matrix then is the Cholesky matrix multiplied by itself, or multiplied by its transpose. And the covariance matrix is what provides information about the correlation in unobserved factors. So if you were to calculate the Cholesky matrix times its own transpose, you would get the following covariance matrix. This is hopefully what you did as part 2 of the problem set. And this is the covariance matrix for the error differences, where you're differenced against the first alternative, which in this case is auto alone. The question now is, how do you interpret this covariance matrix? Is there anything you can learn about these estimates? We know when we look at cost and time coefficients that you can take their ratio and it tells us something about willingness to pay. The dummies for each alternative tell you how desirable that alternative is, holding everything else constant. The explanatory variables we've learned how to interpret. Now the question is, how can we interpret these covariance parameters? It turns out that with the Probit model, it's extremely difficult to interpret them directly. Truly, the only way I've found to interpret them is through substitution patterns, which we'll get to later. But now let's look at this covariance matrix and see if what might seem true actually is true, and we'll find that it's not. So let's look again at the covariance matrix. The diagonal elements tell you the variance of the error differences. 0.65 is less than 1, And so it would be tempting to think, since this is having to do with the bus alternative, and the one has to do with the carpool alternative, you would think that means that the variance for carpool is greater than the variance for bus. That would be something that just looking at this covariance matrix you would think. We know that this is all differenced against the first alternative, which is auto alone, but when we're looking at it just simply from what it is, this is the carpool alternative differenced against auto alone. This is bus differenced against auto alone. It looks like the variance for carpool is greater than that for bus. However, that's not the case, or at least not necessarily. You really can't conclude that from this covariance matrix. For example, if we write out what these equations, the covariance actually is, let's zoom out here so you can see the whole thing. There you go. The question is that carpool variance greater than the bus variance? What we know is that the variance of the difference between carpool and auto alone is greater than the variance between bus and auto alone. That's why the 1 is greater than the 0.65. That's what our estimates are telling us. But each of these two terms involves additional things other than just the variance of carpool and the variance of bus. The left-hand side includes the variance of carpool, the variance of auto alone, and then 2 times the covariance of the two. The right-hand side has the same thing. It has the covariance of bus, the variance of bus, the variance of auto alone, and the covariance between the two. Okay? So just because this is bigger than that does not mean that that is bigger than that. It's possible that the carpool variance is smaller than the bus variance, and yet these intervening factors cause the differences in errors to have the variance pattern that we described. Essentially, you could have a situation where the carpool variance is small, but the covariance with alternative 1 is extremely large, and so you're subtracting out a large number and ending up with a small number, whatever. So you really can't tell what the relative value of the carpool variance and the bus variance. Let's go back to the covariance matrix and look at something else that looks prominent. Here we see that we've got a negative element in this covariance matrix. Again, that would be tempting to interpret as meaning that the carpool alternative and the rail alternative, which is the second and fourth alternatives, are negatively correlated somehow in unobserved attributes. However, again, this is not necessarily the case. If we look at this, wrong one. Here it is. This is the negative term. It's the covariance between carpool and rail. And again, each of those are differenced against the first alternative. And so it's actually equal to the covariance between carpool and rail plus the variance of auto alone minus the covariance between auto alone and carpool and the covariance between auto alone and rail. Okay? This whole thing can be negative even if this term here is positive. So it's possible that the covariance between carpool and rail is positive, but when you subtract out these covariances, the whole thing becomes negative. So you can't interpret that negative element of the covariance matrix of error differences as indicating anything necessarily. The way you do look at it is by comparing with other covariance matrices that have certain patterns, and also through substitution patterns. You can do forecasting with substitution patterns. So we can look at both of those. For example, suppose all the error terms were IID. They were identically distributed. There's no correlation, no heteroscedasticity. Then what would our covariance matrix look like, the one that we estimated? If we have covariance IID error terms, then the covariance matrix for the errors themselves, not differenced, for all 4 error terms, would take the form like this. It's a diagonal element with the same element on the diagonal for all alternatives and 0 covariance. Okay? Then when we take error differences, we're differencing against the first alternative. So we want to find out what is the covariance matrix for error differences when our original errors are independently identically distributed. We do that in the same way that we have done throughout this course by first principles. So we take the variance, we derive the variance for each error difference from the variance and covariance of the original errors themselves. For example, the variance of the second alternative minus the first is going to be the variance of the first plus the variance of the second minus 2 times the covariance of the two. Okay? We know that this is k, and that's 0, so that gives us 2k. We can also look at the covariance between the error difference of the second alternative minus the first and the error difference of the third minus the first. Okay? All we have to do is look at where pairs of alternatives, when multiplied, pairs of errors, when multiplied by each other, give us something not 0. 1 times 3 is 0, because there's no covariance there. 2 times 3 is 0. 1 times 3 is 0. 2 times 1 is 0. All of those are covariances which are 0 in their original errors. The only element that enters non-zero is the error for the first alternative times itself, which has a variance of k. So the covariance of these two error differences is simply k. What this tells us, this is true for all the alternatives in all the error differences. The variances are all 2k, and the covariances are all k. So the covariance matrix for error differences looks like this. Okay? And since we have to normalize for scale, that k is essentially irrelevant. We divide by the top left element, and everything relating to k gets scaled out. What that means is the covariance matrix after scaling starts to look like that, or does look like that. 1's on the diagonal, 0.5 off the diagonal. So if we had a model, if our model had independent error terms for each alternative, independently and identically distributed error terms for each alternative, then we would have gotten this as our set of estimates for something that is only different from it because of sampling variance. Nevertheless, what we got was this. We could do hypothesis testing. In fact, I encourage you to test whether the hypothesis of IID errors can be rejected. I assure you it can, in this case. And just more importantly, though, you can look, just look at this. It looks quite different than the IID error term. So you think there is some pattern of covariance going on, some heteroscedasticity, some covariance across alternatives. But so far, we haven't been able to interpret what exactly it is. So we can say now that we think that it really is not IID error terms, but the pattern of covariance is not quite clear. Like I said, the way to interpret these covariance matrices is through, I think, through doing forecasting. Essentially, when you forecast a change in one alternative, that's going to cause substitution across alternatives, and that substitution pattern will be determined by the covariance matrix. Remember, with the Logit model, you have independent error terms, and what that mainly leads to is the fact that you've got proportionate substitution. If one alternative shifts 10%, the other ones will shift 10%. Okay, so and that's one of the drawbacks of Logit. With Probit, we don't have that. It's the advantage of Probit. But the way we can determine what the covariance matrix is telling us is trying different forecasting experiments and seeing what the substitution pattern is. So what I did in the experiment, or in the exercise, was to ask you to do one particular experiment. Let's do something where we raise the price of driving alone by 50%. Maybe it's a huge tax on gas, another oil embargo, God knows what, but for some reason the price of traveling by auto alone goes up 50%. The question then is, what does this model predict as the shifting away and towards the other modes? Okay. Is it proportionate shifting, as Logit model and IID error terms would indicate, or is it non-proportionate? And what type of non-proportionate is it? Okay. So the first task was to go into the model or into the code and change it so that it could represent an increase in 50% of the cost of the first alternative. Here is how you do this in the code. I will go this line by line. As you recall, vars is the matrix that contains the explanatory variables, and the first one is the cost variable. And it is held in that matrix as number of observations times number of alternatives long. It's one long vector. So what we're doing here is taking that long vector and reshaping it so that it has rows equal to number of observations and columns equal to the number of alternatives. Okay, so we're putting it into a matrix, that one long vector of costs, into a matrix that is number of alternatives wide, 4 alternatives wide. Okay, and we're calling that cost. Then we're raising it by 50%. So you take the original cost, multiply it by 1.5, and you get a 50% higher cost. Okay. Then we reshape it again to put it back in its original form. So this time we're taking the cost, putting it back into a vector which has one column and number of observations times number of alternatives rows. Okay, so we're putting it back into its original form after we've increased it. And then we're just sticking it back into the matrix where we originally got it. So these are the lines that you need to add in the forecasting code to allow the cost of the auto alone alternative, the first alternative, to rise by 50%. Then you simply rerun the code and see what the forecasts are. So I hope everyone did this. What did you find? Well, as you can expect, let me zoom this in a little. There we go. The raising the costs of auto decreases the number of people who are going to take auto. We do have the laws of economics being met, so that's satisfying. Actually, there's a 41% decrease in auto use as a result of this 50% increase in auto costs. That's a elasticity of around 0.8.